In this video, we'll see how we can debug a complex Arduino program by using only the serial port. We'll use a technique called tracing that consists in logging every step of the program to find where the problem is. This technique works very well when a program crashes, but you have no idea why. This is a very simple technique that doesn't require any additional software and that works everywhere, every time. To illustrate this technique, I will show you how I fixed the latest bug in Arduino Jason. On the screen, you can see the Arduino Jason homepage. Now, let's go to the bottom of the page and click on the GitHub link. Open the Issues tab, show the closed issues, and click on the latest one. So, here is our bug. It's a small program that causes an exception on an ESP8260. As with every debugging effort, our first step is to reproduce the bug. Let's copy the program and try to run it. We are now in the Arduino IDE. Let's pass the program, choose the right board, choose the right port, and click Upload. Now, we can open the serial monitor, and we can see that the program crashes as described. Let's go back to the IDE to add some traces. We'll start by adding traces to the calling program, and then we'll progressively narrow down until we find the culprit. First, we'll add a trace here, then a second one there, and a third one here. Okay, let's upload this program. And now we can open the serial monitor again. We need to disable the auto scroll. And here are the traces, A and B, but no C. Only A and B are present in the log. That means that this line caused the crash. Now, we need to open the code of the library and add traces there. We are now in Sublime Text, where I opened the source of the library. This file contains the JSON object class that is used by our little program. Let's add some traces. This time, I will use numbers instead of letters, so we will not confuse with our previous traces. As you can see, it becomes tricky to make sure that every trace is different. Let's create a macro to help us. We need to define this macro before including Arduino Jason, so that we can use the macro in the library. We'll call this macro trace, and we will make it print the file name using __file. __file is a predefined macro that contains the path of the current file. And we will also print the line number using another predefined macro __line. We can now replace the calls to serial.println with our new macro. And we can do the same in the library. Let's upload the program. We can see the traces in the serial monitor. They are easy to identify and are guaranteed to be unique. The first one contains some garbage, probably because the serial port was initializing. We could insert some delay here, but I don't think it's useful in this case. From the traces, we know that line 142 is executed correctly. We need to add more traces to get a better view of the problem. Here is the result in the serial monitor. We can clearly see the path of execution. In particular, we see that in the first case, the program goes from line 304 to 309 and continues. But in the second case, it stops at 304. So we need to investigate further on line 304. But first, let me show you how we can improve the traces again. What I want to do now is to add the name of the function in the trace, so it will be more convenient to read. We can do that by using yet another predefined macro called __ function. Here, you can see the name of the function being executed. But wait, we can do even better. Instead of using the classic __ function, we can use pretty function. It contains the name of the function, as well as the return type and the type of each parameter, so we'll be able to tell the difference between the overloads. In addition, it contains the type of each template parameter, which is very convenient to debug template type deduction. Now, we can see the complete function signature, including the template parameters. However, there is a problem. Do you see it? The traces are incomplete. Indeed, we know that our last line is supposed to be 304, but here it's 325. So what happened? The serial port was sending the data asynchronously when the exception occurred. The exception caused the serial port buffer to be discarded, so a part of the data is missing. We need to fix that. To fix this problem, we need to make sure that each trace is completely written before executing the next line. To do that, we just need to call serial.flush. Okay, our traces are complete now. We can return to our investigation. Let's look at line 304 again. We already knew that it was called twice, but now we can see that the template arguments differ. The one that crashes uses 2 flash strings, whereas the first one uses a RAM string. This information can be very helpful when you're looking for a bug. At this point, I'm sure that you're thinking, wait a minute, there must be a library for that. Indeed, I asked myself the same question, but I checked and I didn't find one. So I decided that I would share this trace macro in a library so that everybody can use it. And that's how I created the library Arduino Trace. Let's try the library. To install the library, you need to open the library manager, search for Arduino Trace and click install. At the time I recorded, the library was not yet available in the manager, but it should be there by the time you watch the video. Once the library is installed, we simply need to include it. Now we can get rid of our trace macro and upload the program. We get the same result as with our little macro, even though the code of the library is a little more complicated. First, it places the strings in flash when possible. Then, it uses some C++ tricks that allows to call trace at global scope. Overall, the library is just 100 lines long, including the comments. Arduino Trace also comes with another macro called dump. It prints the name and the value of a variable. We can use it here to check the arguments, key and value. I will also add more calls to trace to get closer to the cause of the bug. Here, I will save the return value in a variable in order to dump it. Here is the result of the dump macro. It prints the name of the variable and its value. In this case, we can see that both values are correct. However, we don't see the result variable that I extracted in the equals function. Let's go back to the code. From the traces, we know that these two values are correct. Then, we know that this line is executed, but not this one. So, it must mean that strcmp p crashes. Let's see. strcmp p takes one RAM string and one flash string. One common mistake is to pass the arguments in the wrong order. We can try to swap them. And now, let's see the traces. Okay, no more exception. It seems we just fixed the bug. It's time to clean up. We cannot leave traces in Arduino Jason. Let's revert the code to its initial state. For Arduino Jason, I will do a git reset from Sublime Text. And then swap the arguments to strcmp p. For the program, I will just manually remove the traces and upload the program one last time. And now we can see that everything is working as expected. No more traces and no more exception. With this little example, I wanted to show you how easy it is to locate a bug in your program. As soon as you know exactly which line causes the crash, it's much simpler to find the reason. In this case, as soon as we saw that strcmp p crashed even if the arguments are correct, we knew that the function was not correctly called. And the only viable explanation was that the arguments were in the wrong order. Now, this program was running on an ESP8266, so we could have used the ESP exception decoder. Let's see what it gives. I'm going to paste the original stack trace into the ESP exception decoder. The top of the stack points to strncmp-p, a cousin of the strcmp-p that we called. It also shows the function setEMPL that we had in our trace. Unfortunately, between them are unrelated functions and several functions are missing. I don't use this tool very often, because it's difficult to extract the signal from the noise. You never know what is good and what is not. Don't get me wrong, I think that Minodev did a great job with this tool, and I don't know why the results are inaccurate. I'm just saying that this tool alone will not save you from tricky situations, and for these situations I will always go back to the good old tracing technique. So, what are the drawbacks of this technique? Well, first, it's very bad for performance. The program gets bigger and slower, so it's very important that you remove the traces as soon as you fixed the bug. Then, tracing is not an alternative to logging. Logging, possibly to an SD card, is something you do in production while your program is released in the wild, whereas tracing is something you do during a very short period while debugging a program. Of course, tracing is not an alternative to unit testing. I use tracing only when something cannot be reproduced with a unit test running on a computer. The example that we saw in this video involved a flash memory, which is not available on a PC. I hope you learned something. If so, I'd like to ask you a favor. Please try the library. As you saw, it literally takes a minute to get started. If you like the library, please add a GitHub star and share with your friends.